Hello everyone. In this video I'm going to be solving what are called exact differential equations. Uh, these are first order differential equations that take a specific form, and I'll discuss what that form is. Hopefully you recall from maybe Calculus 3 or some vector calculus course you've taken what a total differential is, and perhaps the way we solve an exact differential equation will look very familiar to techniques that came up when you discussed conservative vector fields in a Calc 3 course. If not, hopefully after these few examples, I do have 3 examples here, you'll get the hang of it. Of course, by practicing on your own, right? Not just watching me. Alright, so in all these equations are going to be exact. Now, not every first order equation is exact. Right? You'll see in another video I'll put up. Not every equation is considered an exact equation. But the 3 examples in this video are, and we're going to solve them in a certain way. So I have solved the exact differential equation, and this looks like 2x minus 1 times the differential of x plus 3y plus 7 times the differential of y equals 0. Okay, so before I get into solving this, let me just bring up what is an exact first order differential equation. Do this off to the side. So any first order differential equation is considered exact if it can take the following form. So you have some function of both variables, the independent variable x and dependent variable y, or if you consider x the dependent and y the independent, right? Doesn't matter. Multiplied by the differential of x plus, and then some other function, say n, that depends on both x and y, at most x and y, times the differential of y equals 0, right? Which is what this is looking like right now. But not only that, at the same time, not every equation that looks like this is exact. We also have, and this left side is a total differential of some function. Now, if this left side is a total differential of some function, that means that this function m here is the partial derivative of some function with respect to x. And this n here is the partial derivative of some function with respect to y. Alright, so these would be both first order partials, and if that's the case, their mixed partials should be equivalent, if the function's continuous, of course. So, and at the same time, so not only does it look like this, but at the same time this is, partial derivative with respect to x of some function. So I take the partial derivative with respect to y, which would then be a mixed partial. If that's equal to the other mixed partial, right, and again this is the partial derivative of some function with respect to y if it's a total differential. So I do the mixed partial. I take the partial derivative with respect to x. Hopefully you remember what these symbols mean, right? This m sub y here is the partial derivative of m with respect to y, and this n sub x, right, is the partial of n with respect to x, right? Just shorter notation for partial derivatives. Okay. So let's see that happens here. But all this needs to happen though for you to have a differential equation that's considered exact. All right. So in my equation here, in this example, the m of xy is this function 2x minus 1. And the n of xy is this function 3y plus 7. And then we can verify that this equation is an exact equation by taking partials, right? Take the partial of m with respect to y. Well, remember that means you treat y as the variable and x and any other variable as a constant. So 2x minus 1 here is basically a constant when we're differentiating with respect to y. So my would be 0. And then take the partial derivative of n with respect to x. So again, treating y as a constant, well, hey, 3y plus 7 would then be considered like a constant. This is also 0, and then these are the same. Therefore, this equation is exact. All right, so that's how you'd verify that the differential equation is an exact equation. All right, so again, that means, right, if the equation is exact, that means that this left side here, right, this 2x minus 1 times dx plus 3y plus 7 times dy, that means that this is the total differential this is the total differential of some function we'll call it f of xy. All right. So if that's the case, right, then that means that this f of x, the partial of f with respect to x is 2x minus 1. And the partial derivative of f with respect to y would have to be this 3y plus 7. Alright, and then we're going to use this information here just one at a time to help us figure out what f needs to be. Alright. And then we'll go from there and use that f and the fact that this is a total differential of f to solve the equation. Alright, so I'll start with this statement here. Alright. If the partial derivative of f, this f we're looking for, with respect to x is 2x minus 1, then that means that f of xy, this function f, is, and then what I'd be doing here is integrating both sides with respect to x. I'm integrating both sides with respect to x, right, because I have the with respect to x there. So I'd have f on the left, and then integrating this function, again, with respect to x would be x squared minus x, and then, I'm doing the indefinite integral, so remember, plus some constant. But I'm not going to write plus c, because here, f is a function of x and y, we're integrating with respect to x. The constant, a constant is any function of y then. So I'm going to put, instead of plus c, I'm putting plus and then some function of y. Say g of y, I'm calling this new function. Again, but this is considered constant here when I'm talking about things with respect to x. Right? This is my constants with respect to x. Right. Okay. Well then, now I'm going to take this, so f of xy has got to take this form, x squared minus x plus some function of y. And now what I'd like to figure out is, well, what is this function of y now? And that's where I'm going to use the other partial of f. I'm going to take the partial of this f with respect to y and say, oh, that's got to be equal to 3y plus 7, and that'll help me find this g of y. All right. So then the partial of f with respect to y would be, now going through this form here, again, you're taking the derivative with respect to y, all the x's are considered constant. So this would be 0 minus 0 plus, and then whatever this derivative is, g prime of y. And this should be equal to what we said the partial of f with respect to y was earlier, 3y plus 7. And then taking a look at this statement, g prime of y equals 3y plus 7, and integrating both sides with respect to y, we'll get what this g of y needs to be. I'll say WRT for with respect to. And now this this g of y, it's a function of one variable, right? Just y. So we get g of y when we integrate that equals 3 halves y squared plus 7y, and then plus some constant. All right. But this time the constant's just a number. All right. So again, because this is should only be a function of y, this g of y that we said here. All right, and this is just a real number. All right. Okay, so now that we're done here, well, we're not done. I mean, we have to solve the equation still, but we have this. We have now that f of xy looks like this. Looks like this. X squared minus x, right, plus g of y, which we said looks like this, right, plus 3 halves y squared plus 7y, plus some constant. And it really doesn't hurt to let's just let this constant be equal to 0 for now. All right, so I'm just going to kind of ignore it. So now we go back to the differential equation. We go back to the differential equation. So let me pull this up here. And you see now this left side of the equation is the total differential of our function f. And again, I just have c be 0 to make it simpler. So the left side of this equation now is written simply this way. Right, the total differential of x squared minus x plus 3 halves y squared plus 7y equals, and then 0 is just the total differential of any constant. Right? So this, I'll use c here again for constant. Right? And now that I have both sides written as a differential, we then simply do the integration symbol, right? Integrate, and that'll undo the differentials, and we're left finally with this: x squared minus x plus 3 halves y squared plus 7y is equal to some constant. And here we have an implicit solution, an implicit family of solutions, right? A one parameter family, there's only one constant here, to this differential equation. Right. Great. And you could solve this for y. It's a quadratic, and y, you can solve quadratic equations, but I'm not going to do that, right? Just leave this as it's in its implicit form. All right, and then you've seen me do this in other videos. Again, if you've been watching other videos of mine related to solving first-order differential equations, since this is a first-order differential equation, I would like to show you its direction field or slope field. Now, when I go to do the slope field stuff on the computer, I got to solve for dy dx. So here, dy dx, if I got dy dx alone, would be 1 minus 2x divided by 3y plus 7. All right, so this is what I'm going to enter into the computer to get a slope field. So let me pull that up. Here's the slope field generator in Desmos, and I'm going to enter that expression I just put up. All right, so 1 minus 2x in the numerator divided by, and then 3y plus 7 in the denominator. All right, and then a slope field should hopefully come up. All right, there we go, the slope field. And now I'm going to put in our one of our implicit solutions, and we're hopefully going to see that the solution curve that I put in kind of follows in the direction of all these slope lineal elements of the slope field. So our implicit solution looked like this. Is x squared minus x plus 3 halves y squared plus 7y. And then I had equals, some constant. I'll just use 0 for now, but you could change it to anything you want. And it's taking some time here. And there you go, look at this, see? So here's one solution curve. It's kind of ellipse shape. And you see how it's following the direction of all these slope lines, all these little lineal elements. It looks like it's following in those directions. Looks good. And again, I could replace this constant with anything I want. Say 3. And there you go. There's another one. Negative 2. See what happens there. Yeah. Okay. Yeah. So we have a nice family of solutions written right here. Okay, for any constant. All right, great. All right, so that was an example of an exact differential equation, written very nicely in the beginning. You may have also noticed that this is you could have easily solved this as a separable equation, right? You just take the dy stuff to the other side and you'd have all the x's on one side, all the y's on the other side. It's very clear that this is a separable equation, but we can solve it this way though as an exact equation as well. All right, so that was my first example. Next example, a little more involved. I can solve I'm telling you right now it's an exact differential equation. I will verify that though. Okay, we're going to verify this. Now this is not in the form that I want yet. Right? Remember, the form I want is all the differentials on one side, 0 on the other. Okay, and then we're going to verify that this left side is a total differential. So let's take all the differentials to one side. So keep this x minus y cubed plus y squared times the sine of x dx. Keep that over here. Plus, and then I'd be subtracting this whole thing, so we have minus this, so negative, 3x squared, 3xy squared minus 2y cosine x, and then times the differential of y, and then equals 0. Right. So here I have it in the form that I wish, right, where you have the some function of x and y, this x minus y cubed plus y squared sine x. Again, I'm going to call this m of xy. And this expression here, the negative 3xy squared minus 2y cosine x, that'll be n of xy. And again, I want to confirm that this side is the total differential of some function, what we'll call f. So if it is a total differential, right, this expression should be the partial of f with respect to x. Then we take its mixed partial, right, take the partial of f with respect to x and then with respect to y. So that'll be my. Well, let's see what that is. So the partial of m with respect to y, right, remember to treat x as a constant. So that'll be 0. Then you have negative 3y squared plus, and then 2y sine of x. Remember, sine of x is considered constant here, so it's just going to stay attached. Okay. And then let's see if that's equivalent. Again, if this is a total differential of some function called f, then this expression would be the partial of f with respect to y, and then the mixed partial would be take with respect to x. So I take the partial derivative of n with respect to x, treating y as a constant. So this would be negative 3y squared, and then minus 2y times negative sine x. So plus 2y times the sine of x. And look, they are indeed the same. The mixed partials of this function called f that we'll try to find later are indeed the same. So, this is a total differential of a function called f. This is an exact equation. As I mentioned, right, I already told you it's an exact. I just wanted to verify it and show you how you would verify that. Alright, so like before, right, because this is an exact equation, right, this left side with the differentials is the total differential of a function that, again, I'll call f of xy. And then we're going to find f of xy and then use our differentials and write both sides as a differential and integrate, and we'll have a nice implicit solution, family of solutions to this equation. Okay. So remember, if this being the total differential of f, that means the partial of f with respect to x is this expression here, this m function, right? X minus y cubed plus y squared sine x. And then I integrate with respect to x, right? We integrate, I'll put int with respect to wrt with respect to x. That means, my constants will be y's, there'll be some function of y at the end. And if I integrate with respect to x, you get, f of xy, then, f would be equal to half x squared minus y cubed x. Remember, y is treated as a constant, so y cubed would be constant. And then, remember, the antiderivative of sine, the sine of x, would be negative cosine of x. So we have minus y squared cosine x, and then plus some constant. Now again, the constant here is going to be a function of y, say g of y. All right. And now my goal is to find what does this g of y look like. All right, and that's going to involve n of x. That's going to involve the other partial. Now n of x would be the partial of f. I'm sorry, n of xy is the partial of f with respect to y. All right, so taking the partial with respect to y, we have the partial of f with respect to y would be nothing, right? You're treating x as constant now. Minus 3y squared x minus 2y cosine x, and then plus, g prime of y. All right, and this should be equal to that n of xy, right? The negative 3xy squared and minus 2y cosine x. All right. And we're going to use this to help us find g of y. Okay, so if we have these two equal, now you can very easily see, hopefully, that I can get rid of some terms. Right? If I add 3y squared x to both sides, those are gone, and I add 2y cosine x. So all we're getting here is that g prime of y is equal to 0, and that means that g of y must be some number, some constant. Right? So I'll say c, or that's a constant. Right. So that tells me now the form of f of x, right? F of xy. So f of xy is equal to 1/2 x squared minus y cubed times x minus y squared times the cosine of x plus some constant. We said g of y is just some constant, just some number c. Now again, just to make things a little simpler for the differential equation, a little less writing, I'm just going to have c be 0, because it really won't matter what number that is when I talk about the differential. All right, so now going back to the differential equation, we have our f now. All right, the left side is now, you can see now that it's the total differential of this function here, of 1/2 x squared minus y cubed times x minus y squared times the cosine of x. And again, you can put plus some constant there because it'll just disappear when you take the differential. And then the right side, right, 0, is again just the total differential of some constant. And again, I'm going to use c to represent a constant. And then we integrate, do the integral of both sides, and we have our implicit solution to this equation. So 1/2 x squared, any solution curve that looks like this will satisfy the differential equation. 1/2 x squared minus y cubed x minus y squared cosine of x equals, and then some constant. Right. And here is our a nice one parameter family of solutions, right? An implicit solution to the differential equation. All right, and just as before, let me show you. Hopefully this slope field comes up looking nice. Now when I go and try to find, put in the slope field to my computer on Desmos, I need to find dy dx. I need to find an expression for that. Oh, that'd be pretty simple here. It'd be just x minus y cubed plus y squared sine x divided by 3xy squared plus 2y cosine x. So this is what I'm going to enter when I want to take a look at a slope field. So let me pull that up and see what that slope field looks like. If anything, I'm hoping it comes up actually looking okay. So in the numerator, right, x minus y cubed plus y squared times the sine of x. Make sure you're in radian mode as well, right? Divided by 3xy squared plus 2y cosine of x. And it might take a little bit, but there you go. All right, so there's a slope field showing up for that. And now let me enter down here. I'll put in one of our solution curves, right? Just one member of the family. So our solutions ended up looking like this, right? It was 1/2 x squared minus y cubed x minus y squared cosine of x equals, some constant. I'll just put in the number 0 for now. And look at this crazy curve. But hopefully you can see that, the curve seems to follow the slopes in the slope field. The same, they're following the directions of the slopes in the slope field. And I could replace this number here with any constant I wish, 2. And look at this. Again, they're following, they look like they're following in the directions of these lineal elements of the slope field pretty well. Replace this with anything you want, any constant, and you'll get another solution curve. Okay, great. All right. Now I have one final example. Again, sorry this is running long again, but hopefully you're seeing how to do these. I have one final example where it might, just like I did with this example here, you have to manipulate it just a bit to get it to look like this, this form that I need exact equations to be in. So I've got one final example here. All right. Now this is actually a first order linear equation. So you could solve this using an integrating factor. If you've seen other videos like that, put it in standard form and multiply both sides by some integrating factor and solve it that way. But I'm already telling you that it's an exact equation. So let's get it in that particular form. So we have here multiply by dx. Again, these manipulations I'm doing with the differentials you can only do with first order differentials. Multiply by dx, you have x dy equals, and then the quantity, 2x times e to the x minus y plus 6x squared, all that times dx, right? And then I'll just subtract the x dy, so we get it in that form that we want, right? 2x times e to the x minus y plus 6x squared dx, and then plus negative x times dy equals 0, right? And this 2x e to the x minus y plus 6x squared, right? That'll be that function m, right? M of xy that I've talked about. This negative x is the n, and hopefully you can easily see that this is an exact equation, right? That the partial of n with respect to y is the same as the partial of n with respect to x, right? And both of those are -1. So that means that this is indeed an exact equation. And as I've been writing, if this is an exact equation, that means that this side, right, is a total differential. Let's put TD this time. The total differential of some function that I will again call f of xy. All right. And the partial of f with respect to x, right, f sub x here, should be this 2x times e to the x minus y, and then plus 6x squared, right? And the partial of f with respect to y would be this negative x. Right? So, in the previous two examples, I started with the partial of f with respect to x and integrated with respect to x, and then found the function g of y. But this time, because the partial of f with respect to y is so much simpler, right, so much simpler looking, I'm going to start with that. Right, so this time I'm starting with this, and I'm gonna integrate both sides here with respect to y. Right, WRT with respect to y. So that gives me the form that f will take. So f of xy will be equal to, and again, when you're integrating with respect to y, x is treated as a constant, so this would be just negative xy, and then plus, now not just c, but some function of x. So I'll call this g of x. Right? And now my goal is to find g of x using the partial of f with respect to x. All right. So now, using the way this looks here, right, the form that f of xy is taking, I take the partial of f with respect to x. Right. So that'd be negative y plus g prime of x. Right, and this should be equivalent to what I said f sub x was earlier, right? The partial with respect to x is 2x e to the x minus y plus 6x squared. All right. And hopefully you can see that the minus y's will go away. Right. And now I'm just left with g prime of x equals 2x e to the x plus 6x squared. And we integrate with respect to x, of course. This is all functions of x now. Now off to the side here, remember the integral of x times e to the x with respect to x. If I let u be x and dv be e to the x dx, then du would be dx and v would be e to the x, and I integrate by parts. So it'd be x e to the x minus the integral of e to the x dx would just be e to the x again. Right. So we have g of x equals 2 times this, so 2x e to the x minus 2 e to the x, right, just doubling all this, distributing the 2, and then plus, the integral of 6x squared would be 2x cubed, and then, plus some constant. And again, I'm just gonna let the constant be 0 here for simplicity's sake. So now we have the final form of f, and then we can go back to the differential equation. So f of xy, all right, takes on this form: negative xy plus g of x, which we have found to be this, 2x e to the x minus 2 e to the x plus 2x cubed, and then technically plus any constant, but when we go back to the differential equation, that constant won't matter. Right? So now that I've found this f, we go back to the differential equation. And remember, the left side is just the differential of this function, total differential, and the right side is just a differential of a constant. So I can jump right to my implicit solution set right now, implicit solution family. That negative xy plus 2x e to the x minus 2 e to the x plus 2x cubed will be equal to some constant. And here is my family of solution curves that are solutions to this this differential equation. All right, and then just to see that this looks good. Again, any first order differential equation I can have generate a slope. My computer, my Desmos or whatever, GeoGebra, I can have something out there generate a slope field for. But I need to solve for dy dx. Now going back to the original equation here, all I need to do is divide by x. This would be 2x e to the x minus y plus 6x squared, all divided by x. And I'll put that into my slope field generator. And then we'll see, and I'll just replace this constant with something like 0 or 1, and we'll see a solution curve that seems to fit the slope field pretty well. All right, so back here. All right, so yeah, so I got 2x e to the x minus y plus 6x squared, all divided by x. There's this, hopefully it'll take a little bit for the slope field to pop up. There we go. A little bit of a slope field there. And yeah, put in my one of the members of our implicit solution family. So negative xy plus 2x e to the x minus 2 e to the x plus 2x cubed equals some constant. So I'll just put 0 for now. See what comes up. And look at this, right? Now I know there's not a lot of slope elements in here. Whoever made this didn't make it very dense, but you see how the curve is at points where it's near these lines, these little lineal elements, the curve is pointing in the direction that these elements are pointing, right? It's down and curving up, and you can see again only in the parts where there's actually slopes. Where whoever developed this only developed it to be so big. But yeah, and then I can just change the value of this constant. Changes the curve a bit, but again, the slopes should follow the curve. The curve should follow the slopes in this field pretty well. All right, great. So again, I mean, this is probably one of the few ones where it would be easy to solve for y even. You could get a family of implicit family of solutions. Solving for y would be pretty simple. Just add xy, subtract constant, divide by x, and then you'd have an explicit solution, with y written in terms of x. But I'm not doing that right now. All right. So hopefully going over these three, hopefully watching me do these three examples and practice, maybe practicing these three examples on your own and whatever other problems that are similar to this. I'm hoping this video helps you when you're doing stuff similar to this, solving exact equations. And thank you very much for watching.